Sorry I can't make this any bigger for the MathXL stuff there. I kind of cut and paste. Let's see, we want to, they're asking some stuff about concavity, and then specifically concavity, and then there's some questions in there about just analyzing a function using the second derivative test. Why don't we take, actually we can probably skip this, because the other one, if we just analyze the entire function, then we'll take care of concavity also. So let's scoot up a little bit here. Let's take a quick look at this one. Okay, they're asking us here for this to use the graph of the function f. So this is the function, not the derivative that's graphed, to estimate where f prime and f double prime are 0, positive and negative. Yeah, it's just been a couple days since we've done this. Let's take a quick look at one of these. Okay, so let's take first derivative first here. Somebody estimate. What do you think? Where is the first derivative going to equal 0, roughly? What x value? What do you think? 2, so that's right there.
Oh, I think that might be 1, 1, 3.
Yeah, 1 and 3. Okay, there you go. 1 and 3. Good. So we're looking at it's decreasing. It's doing the opposite, right? Then the slope is going to be decreasing as he's walking along, and the thing is going to be curving out from under him, and he's not going to be able to see where he's going. You can't see over the top of the hump, right? Okay. All right. So we get that one. Okay. What about this guy? Who's good? Take a picture of this so you can see it better. What about that? Use the derivative of the function, y equals f of x, to find the points at which it has local maximum, local minimum, or points of inflection. Now notice they've given you the derivative here, the first derivative. They didn't give you y. They gave you y prime. Okay, so what are we going to do? Take the derivative again. Okay, we're going to need the second derivative, aren't we? If we're going to find points of inflection, we are going to need the second derivative. How would you do that? Just okay, sure. Now, and the question comes up, I guess, do we want to just differentiate? And we got to think ahead a little bit. Do we want to differentiate this using the product rule, okay, as it's currently written, or do we want to expand this thing out? You can go either way, really. Doesn't matter. Now we got to kind of think what's going to happen here. The advantage, if we just differentiate this using the product rule, the advantage is it's going to be written in terms of these factors, which is kind of nice. What if we expand it out? What is it eventually going to look like if we go through all the algebra expanding this thing out? What are we going to get? Just roughly speaking. I don't need anything precise, but polynomial. What order polynomial? What's going to be the highest power of x? Okay, well, what are we going to get first? If we expand this out before we take the second derivative, what are we going to get? Okay, we're going to get a cubic, aren't we? Right. Okay, when we differentiate, we're going to get a second order polynomial. It's going to be quadratic, and that's pretty easy to solve, isn't it? Right? And so probably that's a pretty handy way to do it. Now, what if what if this had been something like x minus 1 to the 7th times x minus 6 to the 4th? Expanding it out would not be a good option there, would it? Even if it were easy to do, which it's not, even if it were easy to do, we're going to get this big polynomial that we've got to solve, and it's hard to solve a big polynomial like that unless we can graph the thing or something, right? But if it's going to be if it's going to be quadratic or less, it's a freebie. We got quadratic formula. We can, we have all kinds of weapons to solve a quadratic polynomial. So okay, so we could expand this out if we wanted to. Why not? It's easy to do. So what are we going to get then what do I do to expand this out? And I'm really just following order of operations, aren't I? Okay, I've got to expand out. If I go down through the litany of order of operations here, there's nothing inside parentheses, but I do have to take care of the exponents first. So I have to expand out the x minus 1 before I can start multiplying, right? So then this is going to look like minus the quantity. What is x minus 1 squared? X squared. Not plus 1. Do you remember that pattern from pre-calculus? If I have a plus b quantity squared, what's our expansion pattern for that? There you go, good. A squared plus 2ab, good. Plus b squared, remember that? Okay. While we're at it, what's a plus b cubed? It's good to rehearse these every once in a while. A cubed, good. Plus 3 a squared b, good. You guys remember how you can always find those, right? There's a binomial expansion that I never remember, but there's an easy way. You can always derive it if you need to, but there's a really easy way for relatively small ones. I showed this to you earlier. Pascal's triangle. Yeah, remember Pascal's triangle? You got the ones down the side, and then the coefficients are always going to be. It gives you the coefficients. The powers always start with all the weight shifted towards the first variable, and then incrementally that one steps down as the other one steps up. But they always add up. The sum of the exponents is always going to be 2 in this case, 3 in this case, right? Okay, so you can probably get rid of that stuff though, huh? So we're going to use this top pattern. And we get x squared, then what, minus 2x plus 1, because our a is going to be an x and our b is a negative 1 this time, right? Times x minus 6, last step. We could multiply out. Okay. So if I were to distribute the negative sign all the way through and distribute the x minus 6, what's that going to give me? Negative x cubed. So negative x cubed plus 2x squared minus x. Now I got to distribute the minus negative 6, so plus 6. Plus, oops, I messed that up. No, that should have been, that should have been a minus 12x, shouldn't it? Yeah. Yes. Okay. Plus 6. And so I get, what, negative x cubed plus 8x squared minus 13x plus 6 is y. Y prime, sorry, y prime. So then, what's y double prime? Okay. Okay, makes sense? And then we can find the zeros of that pretty easily. Okay, so then if we want to find the local minima and maxima and points of inflection, what now? Table. Yeah, let's make a table. Absolutely. And look, this This is great. This is already factored for us. That's kind of nice. Oh, actually, I don't even need, we'll just make a y prime and a y double prime. We don't know what y is anyway, right? Okay, so if we go back up here and we look at this, the problem that we've got to solve, right, if we want to find the critical, or excuse me, the relative extrema, we got to know where the first derivative critical numbers are. So we're just going to set this guy equal to 0, right? Negative x minus 1 squared times x minus 6 equals 0. Well, where are the obvious zeros of that? 6 in, and then when is x minus 1? You sure? Just 1, right? Okay, does that make sense? So we're going to say, I've really got 3 factors there. I've got x minus 1, and x minus 6. I'm just asking the question, when is this double factor equal to 0 at 1? When is this one equal to 0 at 6? So I got first derivative critical numbers at 1 and 6, right? And then what about the second derivative critical numbers? Well, we'd have to set this equal to 0 and solve. What do you think? Was it worth it to expand that out?
Probably not.
I don't know. Tough to say. It would have been kind of nice to just have these written already in factored form too. Either way, not a big deal. If we do want to find these zeros, we could graph the thing, or we could just use the quadratic formula, right? Let's go ahead and pretend we don't have our graphing calculator, so let's set this equal to 0. So if we've got negative 3x squared plus 16x minus 13 equals 0, how would I go about solving that quadratic equation? One thing I definitely want to do here, this. What do I do? Yeah, good. I always, if I'm going to apply the quadratic formula, you always want to have the leading coefficient that's positive. Otherwise, it just creates confusion, right? So let's multiply both sides by -1 to change the signs. Then we get 3x squared minus 16x plus 13 equals 0. What was that supposed to be? No idea. Absolutely no idea what that was. Okay, so then we get x equals. There's a chance to sing. Beautiful, beautiful. So x equals negative b, so I'm going to get what? 16 plus or minus square root. If I square a negative, what do I always do? I don't square negatives, I just square positives, right? If you're going to square a negative, and the reason for that being, even calculus students and calculus teachers will occasionally, if you're putting something in a calculator, especially if it's a calculator with which you're not familiar, and who knows what in your life, how many calculators you use, it's easy to forget to put a negative number in parentheses when you're squaring it on a calculator if you're doing a big calculation. So don't risk it. Whenever you take any negative number in any circumstance, doesn't matter where in your life you do this, if you ever take a negative number to an even power, just drop the negative sign. You know the answer is going to be positive anyway. So 16 squared minus 4 times 3 times 13, all divided by 6, and let's see what we get here. Holy. Okay, so 16 squared was that 256?
Yeah.
256 minus 12 times 13, that's going to be what? 156? Is that right?
Yeah.
All over 6, so that worked out kind of nicely, didn't it? 16 plus or minus the square root of 100. So, right?
That's my sense.
Right, so we get 16 plus or minus 10 over 6. So what's that give us? 26 over 6, that'd be 13 thirds? Or 1. Okay, 13 thirds or 1, those are, and what are those? What did we just find? Okay, well, potential, second derivative critical numbers. So they're candidates, right? We have to check them. They may or may not be inflection points. So 1 or 13 thirds. Let's go back to our table and we can put those numbers in. So 13 thirds, what's that going to be? That's, how's that compare to 6? That's going to be a little bit less,
Yes.
right? Yeah. Okay, and so we had zeros and zeros, right? Okay, so now here's where it gets a little sophisticated. We can be really, that's what's cool in a mathematical sense about it. We can be really slick and work. Where do we want to work on the table? Which row would I prefer to work on if I can?
Oh, second derivative.
Yeah, we want to go as far down as we can, right? And so we're going to have to, in order to test the concavity, we got to know the signs of the second derivatives surrounding these second derivative critical numbers, right? But look, one of the test points we could use is 6, a test point of the second derivative. We'll just use the second derivative test and fill in right there. And then we'll know what this thing is, won't we? Right? Second derivative test will tell us if x equals 6 is a minimum or a maximum. Okay, so let's do that. So if we try a value of 6 in the first derivative, that's easy to do because look, the first derivative is already factored for us. So if I take x equals, I'm sorry, second derivative, whoops, second derivative. Second derivative's right here, isn't it? Whoops. Okay, so the second derivative is not factored, whoops. But still, we can do this pretty quickly. 6 squared is 36, right? So I'm going to get
Negative 108.
negative 108. Good, that was quick. Good. Plus.
Oh,
okay. Plus, what do we get there? 6 times. So that's 96. Is that right?
204.
Okay, so it's definitely going to be negative, isn't it? Right? Because this term is smaller than this one, and this one's negative. Then we can get some more negative. So we know it's going to be negative. So what is this guy right here? If the second derivative is negative, that gives us concavity. We've got a horizontal tangent line, negative concavity. What's that mean? If we did our sketch, I didn't leave myself enough room here to do this sketch. But I'm going to make some. Remember what we said about that? If we have the second derivative tells us if the function's happy or sad.
It's sad.
It's
So it actually is.
Okay, so we got horizontal tangent,
It's
negative concavity. It's a sad function. It's a maximum, right?
It's a sore widow.
So we got to test a value now in between and over here. What's probably a good test point to the left of 1?
0.
Oh, why not? 0, right? And in between, I don't know, 2. Okay.
Nice.
So if we test our second derivative then at 0, that's an easy one.
Negative 13.
Right? Just making sense?
Yeah, so bad.
Okay. If I test the second derivative at 2, that's going to be positive, isn't it? Right? Because isn't it?
No.
2 times 4 something to get.
4, 12.
Oh no, you're right.
Yeah.
It's going to be negative, isn't it?
Oh, yeah. That
Right.
doesn't make sense.
Okay.
Does that mean it's only this is
So hold it now.
inflection? It doesn't change.
Did we make a mistake?
Well, there should only be one inflection.
Are we sure? So
No, I
32.
mean,
Hold it now. This is it's positive. Yeah. That's we about did something impossible there. Everybody see that? It is positive. Okay. So what does that tell us then? Inflection point. Inflection point. minimum. This one was indeterminate, right? Because we had critical numbers. One was a critical number of the first and the second derivative, so it could have gone either way. Turns out, because the concavity switches, it's an inflection point. Now, what if? Just ignore the rest of this thing up here. Just, assuming that we only had, say, just this one spot here. What if that had been negative? What does that tell you?
It's not an inflection point.
It's not an inflection point. If the concavity was negative below and above this double critical number, then what does that effectively tell you about the concavity at x equals 1? Being as the concavity depends on the relationship of a point to its neighbors. Can you have a single isolated point? Think about that now. We talked about this a while ago. Can I have a negative concavity, a single point that has no concavity, and then negative concavity on the other side? Does that make any sense? Because doesn't negative concavity, if it's bowl-shaped down, doesn't that kind of depend on not just that one point, but what's happening around it? It's impossible to affix a concavity to a single point, because a single point has no relationship to any other points, right? And so if that had been negative here, what we would have done is we would have crossed out that 0 and made it negative. Even though it's a critical number, it acts like a negative concavity because the 0 is just kind of a little anomaly, doesn't it? And, right, does that make sense? And so then this would have been a negative concavity and a 0 first derivative. It would have been just like that, wouldn't it? It would have been, okay. But it's not. Inflection point, minimum. Okay, make sense?
Yeah.
Okay, so, we'll keep going through this stuff. It just takes lots of practice. What I want to just take a quick look at here before we run out of time. I want to look at, very briefly, talking about some of the concepts of 3.5. 3.5, pretty minor stuff. What 3.5 has to do with is testing the end behavior of a function. The end behavior of a function, sometimes mathematicians have talked about the behavior at the tails of a function. I think generally now people say end behavior. You want to know what's happening way out there at positive infinity and way out there at negative infinity, because that's important stuff. If you think about where we typically look at functions, we look at one little tiny spot where there's some action going on, but if you were to pull back and look at a function on a big scale, a lot of times they're pretty boring when you go way out in either direction. We want to know what that large scale behavior is, okay? Sometimes we get end behavior that is interesting and predictable. A lot of times the end behavior is a function is just going to increase or decrease without bound, infinite mountain, infinite valley, etc. But sometimes we get a horizontal asymptote. Okay, so end behavior is just a kind of a general way of saying what we're going to come to call limits at infinity, which looks like this. The limit of a function as x approaches positive infinity just means if an ant walks forever in the positive x direction, what kind of behavior can he anticipate? The limit of f of x as x approaches negative infinity says, well, if he trudges on in the negative x direction forever, what can he expect? If it turns out that the function has a horizontal asymptote, so as he moves to the left or the right forever, he eventually butts up against this horizontal linear behavior. The function continually approaches this horizontal line. It may never get to the line, but it always is approaching that line. That's what we call a horizontal asymptote. The look of that would be something like this. And you've seen these before, I'm sure. If I had a function that was doing something like maybe, I'll say it came in, and it was always increasing, but the slope was always getting smaller and smaller and smaller and approaching 0, then we could say that it's maybe approaching some ceiling, some fixed amount. If we go further and further out there, this function's going to adhere more and more closely to this asymptote. Okay? May never get there, but it's always going to get closer and closer, in the same sense that if I cut my distance to the door in half every step, I never actually get to the door, but that's still the limit of my motion. I could have the same kind of thing going on the left, maybe too. Something like that. Okay. Now, we've talked a little bit about vertical asymptotes. Can a function pass through a vertical asymptote? Not a function. A relation can, but if it's a function, it can't do that, right? Can a function pass through a horizontal asymptote? Sure. There's no reason it can't. It doesn't make it a non-function. I could have, for example, let's say a green function that does something like this. Maybe the green function, I'll graph it on, it's got the same asymptote to the right. Maybe it does, oh, it's not green after all, it's blue. Maybe it does that. And it goes through the horizontal asymptote an infinite number of times, but each time it's getting closer and closer and closer. This is like damped oscillations in physics. So that the oscillations are getting smaller and smaller and smaller, and eventually their amplitude is approaching zero when it's just hugging that asymptote. Still works. The horizontal asymptote is still a predictor of where that ant's going to be. If he walks forever to the left, we can say he's always going to be more and more closely approaching that horizontal asymptote, even though he goes through it, right? So, kind of just something to hang on to. Can't cross through a vertical asymptote. Can cross through a horizontal asymptote without, there's no problem. So, if we do get this horizontal asymptote, then we could say that the line y equals L is the horizontal asymptote, or the limit of the functional behavior as x approaches infinity or negative infinity, if either one of these things is true. If the limit of f of x as x approaches infinity ends up being some constant value, then that's our horizontal asymptote, whatever L is. If the limit of f of x as x approaches negative infinity gives us back some constant value, then that also means a horizontal asymptote, because that's what a limit is doing. A limit is telling us, when we take a limit of a function, we're trying to find out what's the y value that we're approaching for a given x value, right? But in this case, it's not a given x value. It's as x increases without bound in the positive or negative direction. These are a little bit different looking limits. In the past, we've always said, what's the limit of some function as x approaches 3? Or what's the limit as x approaches 0, or something like that. Now we're approaching infinity, or negative infinity. Okay, so what's that going to give us if we just try a problem like this? Let's take the limit of this function. If I can make that bigger. I can't. How about that? What's the limit of negative 7 minus 21 over x squared as x approaches infinity? Keep in mind that infinity is not a number, right? Infinity is just kind of a concept. It means big without bound. Well, what's going to happen here to this second term if I let the denominator explode? What's going to happen to the size of that fraction? It's going to get smaller, isn't it? Okay, so if the bottom of a fraction approaches infinity, the fraction as a whole goes to 0, right? So in this limit, that goes to 0, and we just get negative 7, right? So then we could predict, does this function that we've just analyzed, does it have a horizontal asymptote? As x approaches infinity, does the function approach a constant value? It does, right? Let's graph it. Let's just see what that looks like. So if I take I hope this doesn't mess it up. I don't think it will. What was it? Negative
7 minus
21 over x squared. All right, let's try this. Okay, so there it is, right? There's my function. Now look what happens if I pan way back. Ignore the blue one. The blue one's a different function, but the green one, look, it's just flat, isn't it? Now I'm pulling way back here, so these scales are huge. But you can clearly see if I pull back, this thing has got a horizontal behavior when we pan out really far, and that's all we're doing. When we analyze the end behavior of a function, we're just zooming out indeterminately far as we want to, without limit. And this thing clearly, eventually, is really boring. It has this horizontal behavior to it. right? Okay, so what's that? The blue one? Oh, I'm going to. The blue one's a good one. You're gonna like this. So, okay. Okay, so we'll come back to the blue one. Now, what about something like that? So what's going to happen with this guy? If I take the limit of 3x squared minus 2 over 2x squared plus 3. Now, we can do this algebraically, and that's what we'll maybe take a look at tomorrow. For today, let's just take maybe either the numerator or the denominator, and talk about what happens if we take a polynomial and we analyze a polynomial, the behavior of a polynomial. Let's look at a fun one here. What if we take this polynomial, this guy right here? Everybody see that? It's kind of hard to see, but it's x to the 4th over some huge number, plus x cubed over 1,000, plus x squared over 10, plus x. Well, what's that thing look like? Well, I've got it graphed here. It looks an awful lot like the line y equals x, doesn't it? That would lead us to believe that these first terms are unimportant. And that's true. But look at the scale of this thing now. We're zoomed in a long ways, aren't we? We're zoomed in. I'm just going from -1/2 to +1/2 on the x-axis, and something roughly like that on the y-axis. So on a very small scale, that x term is the dominant term. But let's zoom out a little bit and see what happens. We're going the wrong way. There we go. Zoom out a little bit. Well, now what's it starting to look like? Starting to look like a parabola. Okay, so maybe the x squared term ends up being the dominant term. What do you think? All right, we've zoomed out a little bit. And that x squared term, the x squared term had been extinguished initially because it's divided by 10, right? That x squared term, clearly the winner, right? Well, let's keep zooming out. Uh-oh, no, what's going on now? That looks like a cubic. The cubic's the winner after all. The cubic was silent for a while because it's divided by 1,000, right? But eventually the cubic caught up. So is that the eventual winner? What do you think? No, certainly not. If we keep going back, you'll see eventually there, now what's happening? Okay, well, the x to the 4th at some point kicks in, and that's the dominant term. Long story short, the biggest power of x is always going to be the dominant term. If I were to zoom back really, really far, you wouldn't even notice the x cubed and the x squared and the x terms. They'd be just little blips on the radar. That x to the 4th, as x gets bigger and bigger and bigger, it's clearly going to dominate. As x approaches infinity, think about it this way, this kind of heavy concept here. As x approaches infinity, that little wimpy linear term, x, also approaches infinity, right? But the x squared over 10 approaches infinity infinitely faster, doesn't it? Right? If x approaches infinity, a huge number, then x squared is approaching that same huge number squared, a huge number times itself. The x cubed term is going to approach infinity infinitely faster than the x squared term. And finally, that x to the 4th term, once we get out there in the realm of really big numbers, whatever that constant is on the bottom is dwarfed. It doesn't even matter, right? And so it's strictly the power of x that determines what the dominant term is. And when you're doing analysis of a polynomial, when you want to see what the large-scale behavior is, you just cover up everything except the big term. The dominant term is going to be it. The dominant term is going to precisely tell you on the tails of the function, the end behavior, tells you exactly what this thing looks like. Okay. So if we go back then to this question we were looking at, the numerator, as x approaches infinity, what is the numerator going to behave like? 3x squared, right? The -2 has just no significance in the event that we're approaching infinity. What about the denominator? 2x squared. And so kind of a shortcut for dealing with this is equivalent to, and I don't even have to put the squiggly lines here. This is exactly equivalent to the limit of 3x squared over 2x squared as x approaches infinity. And that's a limit we can do pretty easily. What happens to the x squareds? They cancel. And what's my answer? 3/2. How about that? Okay. So then what's that tell you about the end behavior of this function? As I approach infinity, the y value is approaching a constant value of 3/2. So what's that mean for us? Horizontal asymptote. Yeah. Okay. All right.